Okay, so here's our problem again. We have two soil layers behind the wall. We already calculated the active force, net force, acting on the wall, and we decomposed that force, or we had it decomposed, and then we added those forces to get the net force. So we had three forces, one associated with a triangle, one associated with a smaller triangle down here, and then one with a rectangle. Okay, and I have the piece of paper here, like this, right? So these are the forces, and we added them down here. We summed them to get the net active force. So what we're going to do now, well, why did we do that? We initially got these forces because that was the lesson, right? To get the lateral earth pressures, which are these diagrams here, okay? And then from that, get the force, or forces. Get the forces to get the net force. Then with that, we calculated I have it here. We calculated the factor safety for sliding, right? So those forces down here, right? Those forces are well, I guess sum to get the net active force, which is 202.5, right? And the resisting force was calculated in this case as the resisting force that develops due to friction along the base. Okay? The base of this footing there. So what we're left to do is to determine the factor safety for the overturning mode of failure. So overturning means that the soil with the same forces pushes the wall out and the wall rotates. If the wall rotates, it does so in response to driving moments. So those forces that essentially look like this F1, F2, F3, those three forces impose moments about points around, everywhere really, but essentially we have to select a point about which we believe the wall will rotate due to those forces. So when we do analysis by hand, we generally select the bottom of the toe of the wall, which is that point. Let's call it point A. So these three forces produce three moments that drive the failure. Okay, so for example, this force has this moment arm right here. Moment arm 1, right? So we said that this was 0.5. Did we say that? Yes. 0.5, well, I guess the whole wall is 9 meters, and this right here is 2/3 of 6, right, which is 4. Therefore, this is 5 meters. So moment arm 1 is 5 meters. That's for force 1. Moment arm 2 acts 1 meter from the point, from the projection, from the I guess this line here on which the point is lying. So moment arm 2 is 1 meter. It's kind of ugly here, so 1 meter, moment arm 2. And moment arm 3 is this distance here, which is half of this rectangle, because the centroid is right here, and that rectangle is 3 meters, so this is 1.5. This is moment arm 3. Meters, 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 right? So those three moments, if I can write them here, moment 1 is F1, moment arm 1. Force 1, I'm going to copy it from my diagram over here, or my factor safety for sliding sheet. You have it here, right? These are the forces: 96, 10.5, and 96. 96 times, moment arm 1 is 5 meters. That's 4 meters. This is moment arm 1. for force 1. Right? Force 1 produces a moment like that about point A with this arm. So 5 meters. Moment 2 is force 2, moment arm 2. Force 2 is 10.5 kilonewton per meter of wall, and moment arm 2 is 1 meter. Moment 3 is force 3 times moment arm 3. Moment arm 3 is 1.5 meters and 96 kilonewton per meter is force 3. Okay? When you sum these moments, by the way, let's look at the units, it's important always. Kilonewton per meter times meter is kilonewton. So who has heard of a moment with a unit with units of force? Well, the truth is that this is kilonewton meter, which is the unit of moment, per meter of wall. So if you cancel the meters, you get kilonewton, but the truth is that physically speaking, you have a moment per meter of wall into the paper. So this is one value, this is another value, and this is another value. When you sum them, you get what's called the driving moment. The driving moment, sum of these 3 moments, in this case, because of the 3 active forces, is this net moment that drives the rotation. So to get factor of safety for overturning, what we have to do is determine the moment that resists the rotation. So in this case, let's see if I have another piece of paper. Yes, I do. In this case, the moment that resists the moment that resists the rotation is what? Well, if we have moments about this point trying to cause the wall to fail, meaning to rotate, what prevents that from happening, physically speaking? Well, the weight of the wall, right? And the weight of the soil back here. So those weights also have moment arms, and we calculated those weights when we did our factor of safety for sliding calculation. Remember the stem, number 3, the soil back here, number 1, the soil back here above the footing heel, number 2, and number 4 for the footing, right? Each of these components, 1, 2, 3, and 4, in this case, has a weight. So, and in fact the weights are here. Look, you already have this in your notes because you saw this video before the one that you are currently watching. So, for number 1, you have a soil, right? So to determine the weight of this block, you get the area, which is this distance, which is 2 meters, times the height of that block, which is 6. So 2 times 6 times the unit weight of the material that makes that block, which is soil. So 2 times 6 times 18, right? For the concrete components, the stem and the footing, the unit weight is 28. And here are the weights, kilonewton per meter of wall, right? And we had to sum them to get the total weight acting on the base to get the frictional resistance for sliding, right? Over here. But in the case of overturning, we don't have to get the net sum. What we do have to do is multiply those weights times the moment arms that they produce or that they have related to this point, which is the point of selection, the point that we have selected, right? So the weight of the footing acts right here, right? That is the weight of the footing. It's number 4 in our previous sheet. Weight, the weight of the stem is 3. The weight of this part, or sorry, not the weight of the stem. The stem is number 3. The footing is number 4. This block here is number 1, and this block here we call it number 2. So the weight of the footing of number 4 here acts right here at the centroid. Number 1 here. Number 2 right here at the centroid, right? And number 3 stem right here at the centroid of the stem. So what are the moment arms? It's going to get a little messy. Let me zoom in a little bit. Good. Here's the point. So for number 1, the moment arm is that distance, right? The distance from the point normal to the force. So that distance is 0.5 plus 0.5, that's 1, plus half of 2, that's 1. So 1 plus 1 is 2. So moment arm for 1, I'm writing them down here. You'll get to write them in a second. You can press pause. But essentially, moment arm 1 is this one for the weight of this block, which is, we call number 1. That's the force. Here's the moment arm. It's force, moment arm. Moment arm for 1 is 0.5 plus 0.5 plus 1. So 2 meters. Moment arm 2, same, right? This is the moment arm right here. This is the force and this is the moment arm. When I say force, I'm talking about the weight, right? So 0.5 plus 0.5 plus 1, which is half of these 2 here. So moment arm 2 is 2 meters. Moment arm 3 corresponds to the stem. So the moment arm is from here to here. So from this line here where the point is to half of the stem. Half of the stem is 0.25. So it's 0.5 here. So half of the stem, that is from here to here, that's 0.25 plus 0.5 is 0.75. 0.75 meters. And moment arm 4 for the footing is half of B. Here's the moment arm. Yep, half of B is 1.5. 1.5 meters. So these are the moment arms. The forces, I'm going to repeat them over here, or I guess I'm going to copy them from my other sheet, which you already have. You have this in your notes from the factor of safety for sliding. 90, 119, 42 kilonewton per meter of wall. These are the weights. So moment 1 is force 1, 216 times 2 meters. Kilonewton meter per meter. These are moments, right? Moment 2, 90 times 2. Moment 3, 119 times 0.75. Moment 4 is 42 times 1.5. Right? You can calculate this. Press pause and calculate. Okay? And then what you do is you sum. The sum is the resisting moment. Okay, so you have the weights, the moment arms, and notice that all the weights, if you look at the weights here, they produce moments that are clockwise, whereas the active forces produce moments that are counterclockwise, right? So they oppose each other, and that opposition is what leads to the factor of safety. Factor of safety for overturning is equal to the resisting moments over the driving moments. Okay, and this generally has to be larger than or equal to 2 to 2.5, depending on the structure, etc. What matters at this point is the procedure. Now, just to finish off here, you may have, remember from the other arguments that we had here, you may have a tieback, right? And this tieback may be supporting a tension of 100 kilonewtons, let's say, right? And it's located 1 meter from the ground surface, let's say, as an example. If you have a tieback, the tieback pulls the wall back. Therefore, there's a moment that is clockwise. So it's a resisting moment, the one that is produced by this T. What is that moment? Well, let's look at the force. The force is T, right? And the moment arm, here's the point, the moment arm is that, so which would be 9 meters minus 1 meter, that's 8 meters. So you have 8 meters as the moment arm for the tieback. Okay, so the moment due to the tieback is equal to the tieback force. Sorry, let me erase this here. The moment due to the tieback is equal to the tieback force, 100 kilonewton, times the moment arm of the tieback. So 100 times 8. But notice what happens. This is in kilonewton. Kilonewton times meter is kilonewton meter, which is fine for a moment. But we want moment per meter of wall. Therefore, again, what you have to do is essentially divide this. What do you have to do here? This is kilonewton. This is meter, right? Ah, yeah, of course, sorry. You have to take this T and divide it by the spacing. Remember the spacing between the tiebacks? There's a tieback here, there's one behind. So if you look at it from the front, again, what you see is the wall and you see the tiebacks like that, right? This spacing is S. This is looking towards the wall, right here. So the tieback force in kilonewton divided by the spacing in meters times the moment arm, meters, gives you kilonewton meter per meter. So the moment, in summary, the moment due to the tieback is equal to the tieback force divided by the spacing times the moment arm of the tieback, which is 8. So T over S times the moment arm of the tieback. What a mess I have here. Moment of the tieback. Tieback force 100 divided by the spacing, let's say 1 meter between tiebacks, times the moment arm of the tieback, which is 8 meters. Alright, so that's the moment. Apologize for this mess here. That's the moment due to the tieback. Where are you going to put that moment? Is that a good moment, meaning resisting, or is it a driving moment? It's resisting because it's pulling the wall back, causing a clockwise moment about this point. So if you have a tieback or a set of tiebacks, for each row of tiebacks you have a resisting moment here, moment tieback in this case. You have one row of tiebacks up here. See them here? This is the base of the wall. So that means that you have just one term for moment, one term for moment tieback in this equation. All right. Oh, that's last thing. That is a factor of safety, and you can calculate it. Go ahead and calculate it. Use S equal 1 meter. So you have an example in your notes that is completed here. I am kind of in a hurry right now, so I apologize for not being able to. I don't even have my calculator here at home, so it would take me a while to do this. So I know that you can do it, of course. Just fill in the blanks and get the value, right? In any case, when you do that, that would be the factor of safety for overturning for this point. That point is the one that was selected for us for our analysis. So what you would do then is you would say, okay, that's my factor of safety for that point. Now let me put the point maybe like around here. And then run the analysis again and get the factor of safety for that point. And maybe a point down here, maybe a point around here, maybe here, right? So locate it around here because that's where the system is likely to rotate. The lowest factor of safety you get is the actual answer for the problem. And it may be for a point, here. Well, no. It may be for a point down here, let's say, And it may very well be this corner point that we selected initially. So clearly, when you do this in a firm or, at a company or whatever, you don't really do it by hand. You may check your results for one point by hand, but you really do it with software. And you ask the software to evaluate different points, the factors of safety for different points.